Okay. So yes, all those who are online, yes, you and everyone can open. I will just write one of the matrix, that is P0 square, right? That's or X0 square for that matter. So if you look at the Ame's answer, you simply, how do you put it? You put n is equal to 0, right? Then you put n is equal to 1. You will, how it will be represented? So if I'm plotting for X0 square, it is h cut upon 2 m omega, which is common term, right? So rest of the term represents the matrix terms. Fine. So if I put n is equal to 0, what do I get? Aziz, Ame, Shrey, and those who are online, I cannot say everyone's name. Right?
So that would be a diagonal of 1, 3, 5, 7, 9.
Exactly. What about another values? Next term, for n is equal to 1, what do you get?
Sir, I would just like to point out, just in case people are looking at my solution, the first term, the first delta in x square, it should be delta of n dash and n minus 2 instead of the n minus 1 that I have written. So that's wrong in my solution.
That is fine. That is fine. I'm just looking at the rest of the part or the operation part after the operator. Okay. So yes.
So for P naught square, it will be mh omega by.
Wait. Let me see. It will be for P naught square. It will be still within the, if we consider within the bracket notation, it will be minus m h cut omega by 2. That is correct. Under root n into n minus 1 del n dash n minus 2 plus under root n plus 1 n plus 2 del n dash n plus 2. That will be right. That's
right.
mistake.
Yes.
Right. Okay. Minus 2n plus 1 del n dash n. Fine. And the other terms that will pop up will be 0, root 2, 0. Here, what else will be there? Root 6. Similarly, I am not writing the perfect matrix. Yes, this is 0, not 6. Right. Again, here root 2, 0. This 5 should be here. It's not otherwise perfectly diagonal. 5. Here 0, root 6, 0, 7, 0, and so on. Right? I hope you all are now getting. Now you can go ahead. So yes, that equation is correct. You just need to put the value and you will get the matrix. Do we need to look at the problem for time t? Okay, so let's quickly look at the problem. The problem was you had to find xt and pt, right? At that is at time t. Okay, for our harmonic oscillator. So how do we begin? You begin with xt, which was given as, what was the xt given as? Okay, I will just write. It is x0 cos omega t. You begin with here plus p0 upon m omega sin omega t. Right?
Yes, sir.
What will be xt in terms of our matrix elements? How do you go ahead with this? Anyone? Those who tried, you have x0 and p0, right?
Yes.
So you use x0 and p0 over here.
Yes.
So what are x0 and p0? Okay, remember this x0 and dash n, what was it? Under root h cut upon 2m omega under root n del n dash n minus 1 plus under root n plus 1 del n dash n plus 1. Right? Similarly, what was P0? Minus I under root h cut m omega by 2 under root n into del n dash n minus 1 minus under root n plus 1 del n dash n plus 1. Fine. So we then substitute them here in xt. And that's it. You get the answer. Similarly, you begin with pt n dash n x. You have to substitute again that, right? So it will be simply p0 cos omega t minus m omega x0 sin omega t. Okay. Again, substitute p0 x0 here. Right. And finally, you will get your xt is equal to, or do you want to try right now? I can give you 5 minutes. Or shall we go ahead?
So like we can go ahead.
Yes, perfect. Okay, so in short, you will get this particular answer under root h cut upon 2m omega, right? Instead of the elements in terms of their values only, you will have some multiples of e to the power I omega t, right? So it will be under root 1 e to the power minus I omega t, 0, 0, and so on. Then under root 1 e to the power minus plus I omega t. I think this was 0, right? So whatever the values of x0 were, in the multiple, there will be some terms like this. You can look at the trend. What were the x0 values in terms of matrix notation? If you can open and you can compare, you will see it's a simple multiplication. So Ame, so it is not that we are simply multiplying it, we are getting the result which shows that it's a multiple of that matrix element.
Yes, sir.
Right? Okay. Fine. So we can go ahead now. Anyone else with any doubt or any difficulty in problem? Okay, so now let's move to today's final topic. We will not stress today to complete or we will not rush, because I think Bala sir can take up the most of the part because it's big topic, right? Perturbation theory. We will try to see as much as we can in today's class. Okay. So let's begin with time dependent perturbation theory. Okay. So when we say time dependent perturbation theory, what we are talking about is that, let's say we have some transition happening in a given system, right? So our eigenstate is changing from psi I to psi f, right? It is changing due to, let's say, some perturbation within the system. Let's call it Vt. Now this perturbation is time dependent. And it is very small. So we will initially consider a small perturbation or disturbance in our system due to time dependent some potential Vt, right? And that causes our state vector to change from psi I to psi f. Okay. Now let's say our system is in some state of unperturbed Hamiltonian system. So when it is unperturbed, when there is no perturbation, our Hamiltonian is H0, right? So H0 is unperturbed Hamiltonian. Now, as soon as this small perturbation, which is time dependent, is introduced to the system whose Hamiltonian is time independent, or which is unperturbed, we will call it, right? What happens? Psi I changes to psi f. That means our Hamiltonian also changes. So we call our Hamiltonian HT H0 plus VT. Okay. Now let's go back to the interaction picture. So in the interaction picture, so you will need to keep in mind the interaction picture, because that is what is going to help us in understanding, right? Now we begin with what? We begin with our operator UTT0. What is that operator? We call it time evolution operator. It's a unitary operator, right? So we can write this time evolution operator here in interaction picture in this way. So we can write the time evolution operator as UTT0 is equal to U0 TT0 into UI TT0. Right? Now we know about our U0 TT0. Now U0 TT0 is at time is equal to 0. Remember the connection. So it can be given as exponential of minus I H0 into T minus T0 upon H cut. Fine. And UITT0 is the evolution operator in interaction picture. So if we follow the differential equation, the Schrodinger equation, then for UI, we can write the equation as IH cut DUI TT0 upon DT is equal to here VIT UI TT0, right? So what we are doing is, since we know that our U operator is a unitary operator, we will define our potential, which is potential means the perturbation, the small time dependent perturbation, which we in interaction picture we are calling it VIT. So we can define the VIT as U0 inverse TT0 VT U0 TT0. Why? Because our use TT0 is a time evolution operator and perturbation is happening, though it's a small, but with time, right? So this will be very useful. Okay. So now again, let's look at this equation. Fine. How do we go ahead now? Let's integrate. Simple. Right. So let's take IH cut on this side and integrate this equation with time. So let's update it. So going further, by integrating the differential equation from time t is equal to t0, that is t0 to t, it will be dui tt0 upon dt1 dt1. Fine. Now I'm giving this one because I will discuss it later, right? There are certain benefit of writing in that way. We will just see it later. Okay. What will be the right hand side? 1 upon IH cut integral t0 to t vi t1 ui t1 t0. So this is 1 and this is comma. Okay, so to make the distinction, sorry for bad handwriting. dt1, this is 1. Okay. So if you simplify it, what will be the left-hand side? In interaction picture, when you move from T0 to T, what is varying? Your T1 is varying, right? So that's why I have used the T1 and T2. That will be helpful to avoid the confusion. So yes, so T0 minus, exactly. It will be T0, T0. Okay. 1 upon IH cut integral T0 to T VI T1 UI T1 T0 dt. How? Okay. What we will do is that okay. What do you think we should do now next?
Sir, like,
Hmm?
substitute VI of the expression here on the right hand side, right?
You are badly audible.
He is saying that we can substitute the expression for VI of T.
On
Okay. Fine. Let's focus. I want to draw your attention to UI T0 T0. What is our U?
that is U naught.
Huh?
So UI T0 is U naught.
Right. So it's an unitary operator. Okay. So for the simplification purpose, we can consider this to be a unitary. Do you agree or not? Can you see?
That would be the identity operator.
Exactly. Because it's a unitary operator. Right. So we will use that here. So you can mention that we will substitute this with identity that is 1. Right. So that will be very helpful and it will simplify the process further. So my UI T0 will be 1 plus 1 upon IH cut integral T0 T VI T1 UI T0 dt. dt1. I missed 1 in all the expression. Okay, so here what we are getting is we are having an integral equation for interaction picture unitary operator UI T0. Right?
Yes, sir.
Now, if you do multiple iterations of UI T0 within this integral, what do we obtain? We can obtain an infinite series. Correct or not? Because we have said that this perturbation is very small. So if we do multiple iteration, as many as we would like, we can generate infinite series. Right? But
Yes,
what
sir.
we do generally, we simplify the series and we terminate it hardly to one second or third term. That is first order, second order, at max third order. Right? So third order is justifiable. We don't want to go for higher order. It will otherwise cause some mess. Right? Okay. So UI T0 is equal to 1 plus 1 upon IH cut T0 to T UI T1 UI T0. Fine. So how do we go ahead? If you, what should be our next consideration?
Multiply.
Okay, so iteration will happen in which particular part? Potential perturbation is small. It has occurred, right? It's very small.
Yeah.
Here, what is UI T0 is there? So iteration of UI T0 is what we are going to do within the integral, right?
Yes.
So what will it give us? Okay, so let me write it again. So again, okay, going ahead from this point, we are going to do repeated iteration of UI T0 within this integral. Okay, this is very small part. Keeping this in mind, let's write the first term. So first term, I will keep ui, okay, left hand side, ui t t zero as it is, 1 plus 1 upon ih cut integral t0 to t, simply vi t1 dt1. The next term will be 1 upon ih cut squared integral t0 to t dt1 integral t0 to t1 dt2 v1 t1 v1 t2 into ui tt0. Seems little complicated, but it is not that much. You can take a minute to understand. Again, I am repeating, ui t0 is considered as unitary. And what we have done in the integral, let me use laser. Within this integral, we are doing repeated iteration of ui t0. And we are avoiding the higher order terms because contribution है ही नहीं VIT का, right?
Yes.
So now, so T1 and T2 are simply for the sake of understanding the terms. Okay. Here, this T1 and T2 I'm talking about.
मतलब आपने सर सब्स्टिट्यूट कर दिया ना
हाँ हाँ बस simple. Correct. So what happens next? Again, if it's a unitary operator, right? So we are actually left with what? Okay, you want to, okay, before I go to the next term, let me, those I think some may not have understood what I am trying to say in terms of iteration for ui tt0 is that I'm trying to say that we are going ahead like this, summation n is equal to 0 to infinite ui to the power n tt0, right? And we know that ui at t is t0. Remember, t0 is unitary. With this in mind, what happens to now here? I am focusing. I'm again going for here within the integral, right? So this is the that part that I am trying to use in words. So ui and tt0 will be ih cut to the power minus n, right? t0 to t dt1 integral t0 to t1 dt2 and so on up to how many terms? Nth terms, right? We can go to infinite terms, but we terminate to some term here. So in generic term, I will write it to tn minus 1 dtn vit1 vit2 and so on up to vitn. Is it clear? With consideration that the contribution is from the initial term, right? So T1 will be greater than T2 will be greater than T3 is greater than Tn. That's what you have to consider. So the time evaluation operator, that is our UTT0, is U0 TT0 UI TT0 when we do the expansion in terms of series is this. I hope it is now coming to the full circle. Fine. Okay. Further, if we expand it further, if you want to understand in the interaction picture that we are talking about, so I will further write it. See, if we use this now terms, generic terms, IH cut square 1 upon IH cut, the generic version that I just written here, right? Let's use this. Okay, let's make more clarity. We don't need to rush today. Fine. So this UN TT0, you may see that I'm repeating again, but it is, I think, required to have better understanding of the operator to TT0 UI and TT0, right? What is it? I h cut to the power minus n, T0 to T1, dt1, T0 to T2, dt2, T0 to Tn minus 1, dtn u0 t t0. Into in the continuation of here into v1 t1 v2 t2 up to we have not given the potentials name, right? So we will keep it all VIs. VI and VITN, sorry. Okay. So this is
Excuse me, sir.
Just
a small doubt. In the last multiple integrals at the bottom of this page, should the
here
upper limits be shifted to the right? I mean, should the first upper limit be the variable t?
you're talking about T1 and T2 and so on, right?
Yeah. The first upper limit you have written as p1. My doubt is whether it should be just t and the next upper limit.
Oh, yes. I have repeated it 2 times, right? It will be T, yes.
Okay, so that was just the doubt.
Yes, no, that's correct. Very good. Okay.
Sir, one doubt, sir.
एक minute. No, we need to check. हाँ, बोलो बेटा.
So this in the above equation you have written u of t naught as this multiplied
Here.
by ui. How does that become, like, how do you justify the next equation that it will be u naught multiplied by ui of that? Why doesn't u naught have a subscript of n? Why is it same for all? That's my question.
Okay. Yes. कौन? Hello. Fine.
आप मुझे काम कीजिए.
I think someone is not mute. Aziz, can you just mute someone from the yes. Okay, so let me do the exercise again. Fine. The point over here is step by step we will go. Okay. We just now begin with very first part, that is here. Your concern is from here, right?
Yes, sir.
Perfect. So let's begin to understand even this equation. That's why I was working out with this one. So you understand that we are working with that order, right? And order or the terms for the unitary operator. So if
Yes, sir.
UNTT0 is the order, then from the UTT0 definition, it must be due to the interactive picture part, right? So U0 TT0 is as it is. This is UI and TT0.
Right. Okay. So
Fine.
the order of unitary operator only arises because of the interaction term.
Exactly.
Okay. Yeah. Got it.
Fine. So that's so understand this to get here. It's what we can say is that we have to go forward and backward, right, to see the larger picture. Here we are going in this way, then we will come back to again this above equation, first equation, differential equation, right? Over here. Okay. So yes. Okay, going ahead. So UNTT0. Further simplification will give us minus nth power integral T0 to T dt1, T0 to T1 dt2, and so on, T0 to Tn minus 1 dtn into U0 TT1 into VT1 into, I'm writing the terms one by one, right? U0 T1 T2 VT2 and so on. Last term or the second last term will turn out to be U0 Tn minus 1 Tn Vtn and finally into U0 Tn, this is U0 Tn T0. Now this last step, if you look at this last step, which is U0 Tn T0, okay, or if let's not directly jump to the general case, let's look at the first term in the last step, that is this. Okay, let's begin with here first. So that is U0 T0 into Vi T1, right? It's again unitary operator, U0 T0, U0 inverse, T1 T0, VT1, U0 T1 T0. Fine. Okay, now it is perfect. Now, this will be equal to U0 T0, U0 T0 T1, VT1, U0 T1 T0. Why? Because that's what we defined earlier in the beginning of the discussion here, right? Here. Okay. So with the help of this and with the help of the previous derivation for UNTT0, which is this. I know now there are too many equations, but just wait to see the result. So this will turn out to be unitary operator U0 T1, potential T1, U0 T1 T0. Okay, so that is our U0 T0 Vi T1. Similarly, let's look at, so let's do one similar exercise for the second term in the last integral, that is U0 T1, this is 1, okay, T1 T0 Vi, this time T2, right? So we can write it as U0 T1 T0 U0 inverse T2 T0 V T2 U0 T2 T0. This will transform the terms into U0 T1 T0 U0 T0 T2 V T2 U0 T2 T0. So that is U0 T1 T2 potential T2 U0 T2 T0. Okay. Okay, so there are now too many things that we have done mathematically. Let's discuss something. Then I think we should go ahead. Fine. Now, I will show and try to explain this graphically because you have heard the term, maybe you have read it. That's where we are heading after just a small discussion. Okay, so just give me 5 minutes. Fine. Okay, the equation that I am looking is
So just one doubt.
yes.
The terms you have written down are U naught, no, below, sir. The terms that we finally derived are U
Right,
naught T2 comma T naught multiplied by VI T2, right? The
T1,
second
T1,
one.
it's a T1, sorry.
So
This
this
is T1.
T2, T1. Okay,
This is
then
T1. This is TT0, the first one.
yes, this is
This is comma, sorry.
yeah,
This is
this
not
one.
one.
Yeah, this second one is T1, T0.
Yes. From
But in
TT0 to
the
T1, T0.
yes, sir. But in the integration,
Yes. We are begun
we
from
have
T.
T1, T2, right?
No.
Here.
We are beginning from T.
No.
Then
That's
T1.
fine, sir. The terms.
The final integral terms.
Yeah, the terms are U naught T1, T2 multiplied by VT.
Okay. Okay. I got your point.
No, I'm
See,
just asking if that's the correct
No.
thing.
You are correct. You are correct. What the terminology is secondary, right? 1, 2, and
Yeah,
0,
yeah,
1 that
yes.
has shifted, but otherwise, I hope that you are getting how we are heading
Okay,
towards that.
fine. But
Right. So
yeah.
if I will go to correct now everything, we will waste.
No, that's fine, sir.
time.
I'm just making sure the integration terms are the correct ones.
Yes. They are the correct.
Okay.
one.
Yeah. Okay.
Or what we can do is that what you can do the re-derivation using
Yeah.
the separate terminology, right? So
Yeah,
to
sure.
avoid any confusion.
Yes, sir.
Okay. So I was saying yes. That UTT0 that we defined for the interaction picture when it comes into the play, right, is when we are considering that our perturbation is very small, right? And that's why we are doing series expansion, right? And if we want to do the series expansion, then we know that our wave function is also in interactive picture, dynamic variable and wave function, that is state vector, they are both changing, right? So our psi t, it is also affected by the time evaluation operator. Correct? And we can simply, it can be rewritten as UTT0 psi 0. And generically, if we are since considering the series expansion of unitary operator, we can write it in the terms of n orders of state vector terms as, right? So our psi t is equal to summation n is equal to 0 to infinite psi n t. Now even in books, generally you begin perturbation theory with this one. So this is the reason why you write it in this particular way. Okay. And psi t0, and if you want to work it more generically, what is psi nt, right? Then psi nt will be what? It will be un order tt0 psi 0. Okay, so the point is, let's begin. I will speak in the terms of words, right? Let's not think about now operator. How did we begin? Let's look at the journey. Today's class, we considered let there be some transition happening, right? Which is happening due to introduction of some time dependent perturbation potential Vt. So our eigenstate changes from psi I to psi f. Before perturbation, Hamiltonian was H0. Due to the small perturbation, Hamiltonian is Ht. We begin with our time evaluation operator, right? Introduce that. Okay. Now UTT0 due to interaction picture will be U0 TT0 and UI TT0. Let me scroll along with when I'm speaking. Right? So this is what we say. Where our U0 TT0 is this particular term. And since it's an operator, we said, okay, we can use the technique that VIT can be considered as U0 inverse VT, U0 TT0. Very useful, right? It has been very useful. Then we went for the differential equation, Schrodinger equation, where we substituted the interaction picture, unitary operator, along with the perturbation here, because that's the part of Hamiltonian, which is changing Hamiltonian from H0 to HT, which causes psi I to psi F. Okay. So then we were left with this within the integral, right? This T0 we considered that, okay, it's a unitary operator. It's at time t is equal to 0 in Schrodinger picture. We can consider it unitary. We made it more simpler. Fine. Then we decided that, okay, in the integral, in the last part of the integral, where we have this UITT0, right? What we can do is that we can have a iteration of UITT0, right? That will occur within the integral. So we can obtain some infinite series. And since perturbation is smaller, the successive term contribution will be lesser and lesser. And so we decided to terminate it to some terms. And that's where we return up to this equation, right? We substituted and we return up to few terms only. But this infinite series due to the iteration, how did we reach that? That's where we began the discussion from our UITT0 in interaction picture. Fine. Considering that at t is equal to 0, it is unitary. Of course, that's what, so we considered over here as well. Fine. Going ahead, for the higher order, this is the discussion for the evaluation of time evaluation operator for the Hamiltonian, right? So when we consider it for the Hamiltonian update, we have to consider this entire part. Then we solve the integral further and further, right? We are left with these identities. What they all suggest is that, okay, the evaluation operator is evolving with time, and it is providing us how the perturbation term is going to change with time. Now, since it's an interactive picture, psi is also going to change. So we introduce psi, right? Which is due to the time evaluation operator. So first we understood how the time evaluation operator operates along with the small perturbation for some terms only. Here, two terms we have considered, right? And we are also now looking at the state vector, that is wave function, how it is associated with the unitary operator, that is time evaluation operator. And this is the expression that we have reached for our side t. This is t. Sorry for bad handwriting. Okay, so now when we said time evaluation operator for Hamiltonian for all the order of time evaluation is considered with consideration that potential is having small contribution, right? What we see that psi operates or evolves in this manner. How do we understand it? We will now see Feynman graphs, right? I don't know whether you are aware about Feynman graphs or not. Okay, so remember, where was our system? Our system was initially at Hamiltonian H0 system, which was unperturbed system, right? Then it undergoes interaction with time. So here we use the time t, t1, t2, and so on. And similarly, potential t2, t1, t3, and so on, right? So the unperturbed system undergoes interaction, let's say v t2, t2 times. Then it continues to evolve by our operator u0, t1, t2 to the next stage, right? Till time t1. Then again, it undergoes interaction at potential vt1 at time t is equal to t1 and reaches the final stage from psi I to psi f at time t. Okay, so let's understand with the help of Feynman graph. So it's a Feynman diagram which is depicting zero, first, and second order contribution in the terms of time evolution operator. So let me change this color scheme, right? So it will look better and we can understand it nicely. Okay, fine. So this is, let's say, one state, this is another state. State vector psi, when I say state. So at t0, this is psi 0. And at t is equal to t, this is psi t. Right? So what happens first? When there is time t is equal to t0, what is associated with psi? So here, if it's a psi 0, it is due to, let me even, I will change the line to yes. So first journey in this direction. Fine. It will be with the help of what? Can someone tell me? With our time evaluation operator U0 T T0. When we move to T1, so it should give us psi 1. How will it evolve? What will be now your unitary operator? How will it change? U naught T T1 and U naught T1 T0. Exactly. Right. So it will evolve actually. So we said it in a reverse point of view. It is already from T to T0. Right. So here it's T. Listen, T is over here. Right. So it will be in two parts. So let me draw two parts. So this is one part. This is second part. Right. So how it evolves is that now this is our evaluator operator U0 T1 T0. Here is our perturbation with T1, right? And it happens to become then U0 T T1. Clear? Similarly, at psi 2, how we are going to go ahead? There will be 3 changes in the terms. In which term? I'm talking about unitary operator or time evolution operator. Right? So it will go in this direction. This is very random, right? Don't take this very literally. This is for the sake of understanding only. Yes, but they are Feynman diagram, right? Right. So here the perturbation is VT2. Fine. And your operator, how does it evolve? Come on.
T2, T1, T1, T0.
Exactly. Right. So U0, T1, T2, U0, T1. Remember why this is the case? We said that T1 is greater than, T2 is greater than, T3 is greater than, so on, Tn. Fine. So this is our Feynman diagram depicting 0 first and second order contribution to psi t. Okay. Ooh, we have not yet discussed perturbation yet. So perturbation discussion begins now. Once we have understood the operator, right? So now what happens? Now comes the discussion on first order perturbation. Right? How does it happen? We simply consider the first order. So your psi t is simply now psi 0 t plus psi 1t. Okay. And then you do all the bracket notation. You begin with let psi 0 be. I think some of you may have already studied the perturbation, so I'm giving you the hint. We don't have time to go into the details, but yes, how do you go ahead now? So you now assume that, okay, we are now in eigenstate, in initial state, where the Hamiltonian is H0, the initial wave function is psi I, right? And then it is psi f after the perturbation. And then you will begin with the transition amplitude. So you will write the bracket notation of psi f, psi t, right? What is the happening? And then you will introduce your unitary operator here, but you will be using it just for the operation purpose only. You will also need some psi 0 at the initial case, right? So you consider some ui e to the power minus I e I t upon h cut square, or sorry, upon h cut, correct? And you will begin with some psi f with uf is equal to e to the power minus I ef t upon h cut. And then you substitute them in the amplitude matrix notation, right? Transition amplitude, you find it, and you have the finally some basic equation that provides you the contribution of time dependent perturbation, right? So you call it the first approximation and so on and so on. So yes, let's keep it up to this point. There are so many things that follows now. The first order perturbation, then there is constant perturbation, then there is continuum, transition to continuum, right? And when you are introduced to scattering, it will take you to another level, right? Then there is harmonic perturbation. There are adiabatic and sudden approximation. So now you can, with this concept in mind, once you have this idea, once you have this mechanism at your hand, now you can take anything. So now you have in the tool to go ahead with any perturbation theory. With this, I conclude my lecture today. Let's go for Q&A.
Thank you. Thank you.
Okay. Yes. Okay. Okay, everyone. If there is no question, hello.
Yes, sir, we can. Yes.
I think, am I visible? Okay.
Yes, sir.
Perfect. So any questions, any further discussion you want to do, you can contact me, right? So this is our time for today. Tomorrow onwards, Dr. Bala sir will be taking your class. He is also extraordinary in the quantum statistical and quantum mechanics, right? So most probably he will take some of the perturbation theory. I will share him the details of today's class, and he may take up ahead from here, or he may take you to another journey or his point of view on certain other. Oh, Bala sir is already here, sir. So you got the gist, right? What we have covered.
Yeah, I got the gist. I would also like to know what are the students' interest and what they would like to cover.
Yes, perfect. So that is going to be helpful. Bala sir is already here, students. So please discuss with the sir. Be free to interact, right? What you want to cover in the upcoming class. Sir, I have just given them, we have not covered the perturbation, just as you have seen, simply the operator, use of the operators only.
Okay, I will try to take over from there. And because you have started with the word perturbation theory, so I'll try to get into perturbation theory.
Exactly, sir. Yes, sir.
The time dependent one itself.
Yes,
and
sir.
maybe in the later half, I will try to get into time independent perturbation theory. But
Okay,
generally, the idea would be to deal with time independent perturbation theory first and then go into time dependent perturbation theory. But since you have already, let me see how it goes about.
Okay, sir.
That's what I would like to cover tomorrow. And then maybe try to get into some applications associated with that. Applications in the sense some of the results like Fermi Golden rule and so on and so forth. Okay, regarding transitions due to perturbations and so on and so forth. And in the next lecture, I would like to touch upon the theory of scattering.
Yes.
on the on Friday's lecture. Okay. Apart from this, if the related to this or apart from this, if the students have, if they have any request, what I should be covering and what details I should be covering, I think students may ask. And if time permits also, just for completeness sake, for quantum mechanics, I'll go through the, hydrogen atom derivation. I will not take it as a hydrogen atom problem solution derivation. I'll take it as solution of the Schrodinger's equation in three-dimensional problem and solve it in spherical polar coordinates. But one of the solutions is towards the hydrogen atom solutions. And if you replace the potential, you will get, three-dimensional harmonic oscillator solution for, the nuclear shell model. Okay. So in that sense, that I will get into if time permits. As such, I will try to continue with what Abhishek ji has started out and get into perturbation theory and then get into scattering. And towards the end, if time permits, I will
So
get
there is a chat. Some student is trying to say that if the WKB can be covered.
Okay. Yeah, I just read it. WKB method you would like me to cover. Okay. Any other queries?
Sir, 2 lectures, I think. I told them that the 5 lectures are not enough to touch up even some topics as well. Right? We can hardly do the justice to subject.
I'll try to get into WKB approximation and let's see how it goes.
Okay. Okay, sir.
So I will be mostly trying to, I will not be using a pen presenter kind of thing because I don't have it here.
Okay, sir.
What I'll be trying to do is I'll be trying to put all my lectures into slides.
Right, sir.
And all the equations I'll be trying to put it into slides, and accordingly we will go through it.
Okay. So
Okay, everyone. So I think this concludes the class. You all have, I'm in the WhatsApp group. You can contact me regarding any discussion if you want to do follow-up discussion or if you face any difficulties, right? Okay. My best wishes to everyone. Yes, sir. Please continue, sir.
No, there's an unhappy face among the audience there. The third person behind.
Aziz.
Yes, sir.
No, sir. He's smiling.
Okay. I'll get back to him separately.
Okay. So yes, thank you everyone for listening with good focus and participating in discussions and doing the work at home as well that was given to you. I'm very happy. Okay. So yes, all the best everyone. Best wishes for the successful future in theoretical physics. Right. Even myself. Yes. Okay, Sachin. Thank you. Myself, I'm working in experimental, but I like physics in general. So yes. Anytime you can contact me for any discussion in future as well. Okay. Thank you. All the best, everyone.
Thank you.
We can conclude the class.